Hey guys, I'm going to be using the notes a little bit today, and then adding some other tables in. Again, that maybe you want to write down, maybe don't. It's pretty easy stuff today to finish up 3.1. Kind of be starting kind of in the same place we were at. Just talking about independent variables, inputs. What x is, how that makes up the domain. Our outputs are our dependent variable. Our y's, and those make up the range. And that idea of what a function is, that with a function, when we put in something, we always want to get that same output back out. And so that if you think of that idea that something could malfunction when you put in a certain input, again, that idea with like the soda machine, that if I hit the Pepsi button and a Sprite comes out, that I would say, oh, something is malfunctioning here. So every time we plug in 5, we want to get the same answer back out. Every time we plug in 2, we get the same answer back out. So what we're looking at today is how do we know if a relation is a function? And so it's just based off that, right? When we look at an input, it should only have one output. So in this particular function, the input would be 5, the output would be 4. The input would be -2, the output would be 3. The input would be 1, the output would be 4. The input would be -5, the output was -2. So from what we can see, every input has only one output, and it does not matter that these two inputs have the same output. Again, the idea that you could have like 2 Pepsi buttons on the machine, and they both, 2 different buttons give us the same output, which is fine. So from what we can see, that this, this one would be a function. Okay. Same thing down here on example 3. From what we can see, 1 input, 10 output, 2 input, 100 output, 3 input, 1000 output. So from what we can see, this is a function. So here's a couple examples that you guys don't have, and again, you can choose to write them down or not. Coming out of your textbook. So here's first table, looking at the inputs. 1 goes to 8, 2 goes to 6, 3 goes to 7, 4 goes to 6, 5 goes to 8. So, from again what we can see, since we're only seeing each input once, they appear to only have one output. So again, it's okay that the outputs are the same. So this one would be yes. That one is a function. And the second table here, so 5 years is 42 inches. 5 years, 5 years is 40 inches. 5 years is 42 inches. 6, 7, 8, 9. So here, really what we're looking for is that the same input giving us 2 different outputs. And so this particular table would not represent a function. So it's still a relation, it's just not a function. Same question here, are any of these tables functions or not? So 2 gives us 1, 5 gives us 3, 8 gives us 6. So from what we can see, that this one is, yes, a function. Here, -3 gives me 5, 0 gives me 1, 4 also gives me 5, but again, that's fine. So each input only has one output. Yes, and then the last one, 1 gives me 0, 5 gives me 2. Next time I plug 5 in, it gives me 4. And so then this one would be no. Again, 5 has 2 outputs. How do you know if something is a function or not from its table or table of values or list of values? Head back to your notes. I think this is on the next page of the 3.1. So graphically, how do we tell if something's a function or not? We have what's called the vertical line test, and you guys definitely should have seen this before. So the idea is that if we draw a vertical line anywhere on the graph and it touches the graph more than once, then that is not a function. Okay? So the idea is that if there's anywhere I can draw a vertical line, and so I've just kind of sketched out some graphs here, just one that kind of looks like would be like maybe like a sine wave, one that's like an ellipse, and then one that's like a parabola on its side. Okay, so sketching those out. So if there's anywhere on there I can draw a vertical line and have it hit more than once, then we have an issue, right? So I draw that one and it only hits once. Draw that one and it only hits once. Draw that one and it only hits once. So it does not seem like I could find anywhere to hit more than once. So this one would be yes. And it passes the vertical line test. And I would just abbreviate that VLT. Second one, pretty much anywhere I draw it, if I could come over here, I'm not even hitting the function at all. If I try to draw it right on the edge, it might only hit once. But again, it's kind of cheating that process. It's really to see if anywhere we hit more than once. And so yes, this one would not be a function. It would fail the vertical line test. And same thing over here. There's definitely a place where we could hit that graph more than once. So, why does the vertical line test relate to functions or not? So the idea is, how do we know if something is a function or not? Is given a certain input, is there only one output? So the idea is, if I plugged in 1, so if I said, hey, what's f of 1? Well, then the y value could be, I don't know, whatever that is, like 4, right? Doesn't really matter. So we can say the y value is 4. We can also say that f of 1 gives me a y value of -4. So we can see that from one input we could have 2 outputs. And so that's why the vertical line test lets us know if something is a function or not based off its graph. So one input could still have 2 outputs or more outputs. Right. Here we can see that each input only has one. Each x only has one corresponding y, right? Each input only has one corresponding output. A couple more graphs that you guys don't have, and again, you guys kind of decide if you want to draw them or not. We're just kind of scattered points randomly around. There's really nothing specific about what I've done here, besides one thing. And again, just from what would be called a discrete graph, where it's just individual points. Can I see if it's a function or not? So basically, we're looking for the vertical line test. So is there anywhere that I'm hitting more than one point with a vertical line? And this particular first graph that I've drawn, just kind of again randomly, none of those vertical lines hit more than one point. I come over here once. Oh, now I've hit 2 points. Okay, so kind of seeing what is here is that, see these stacked points. So if there's any points that are stacked like that, then you would know that that would be a fail. So this one would be pass. Right? So looking for stacked points would tell you that that's not a function. If any of the points are not stacked, then that is a function. All right, so that's kind of it for the lesson. This next part is something that you guys need to be working on. It is going to become a big thing for some future lessons, so you guys to start doing this. This is, I think, what this textbook calls your toolkit functions. I think, I've always just heard them called as, the parent functions. And if this was something, we're in normal year, I would have you guys, I'd teach you guys these, go over these with you guys, and then be quizzing you on their shapes and things like that, because of how important it is to be able to recognize the shape of a function, or the function based just purely off its shape, as we move into future things, especially as we look at like things like piecewise functions and things like that, and as we're graphing and doing other things like that. So it's going to be somewhat of an expectation that you guys are starting to learn these, because it really is going to be very hard to move through some future things if you don't recognize a function by its shape, or as you're trying to graph something that, does my graph make sense based on, does it fit the shape that it's supposed to be. So just kind of, I guess I would say word of the wise that this is something you guys are going to end up needing to know, that when you see a picture like this, like, okay, there's an absolute value function, or when I see a picture like this, okay, that's a cubic function. So I guess just kind of, that's going to be an expectation that you guys start to learn these, memorize these shapes, and then there's going to be some other features and then we're going to build on next lesson in 3.2. So, and then 3.3 also is going to deal with these. So the first one being the identity function, y equals x, it's just a linear function. So the identity function is linear. And all I've done here to draw this is just, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, right? Negative 2, negative 2, negative 4, negative 4. So 10, 10. So you can see why it's called the identity function, because the x and y values are the same. They are identical. So that's the identity function. It's linear. It's the only one that has like a special name that's different than just what it is. Then there's the absolute value function, which is a v. Okay? And then, of course, the vertex here at 0, 0. And you can see that it goes up to 10, 10. I guess that's a 9, 9, actually. Sorry. Negative 9, negative 9. Of course, absolute value being what absolute value is, that we always end up with a positive answer, even though we have negative inputs. But it's a v. And then our good friendly quadratic function, which of course is a parabola. But it's more of a U shape. Again, we have our vertex at 0, 0. Then we go to 1, 1, 2, 4, and 3, 9. And then of course negative 3, 9, negative 2, 4, and negative 1, 1. Those are the points I'm plotting there. So x squared, so that parabola shape, you guys definitely spent a lot of time talking about before. Then cubic functions, you guys would have spent some time talking about, but not as much. I always think of this one as like a vertical S. How I remember it, vertical S. But again, so we don't have a vertex here, but we have a center at 0, 0. Then 1 cubed is 1, and then 2 cubed is 8. So I think 2, 1, and 0. And then of course we go to the other side, which would be negative 1 and negative 2. Negative 1 times negative 1 times negative 1 is negative 1. And then negative 2 cubed is negative 8. So again, it can sometimes be helpful to know these numbers that are easily cubable. As far as, that also still fit, because 3 cubed is 27. So very quickly we run out of numbers that fit onto a nice little 10 by 10 graph. So cubic function is vertical S. Reciprocal function, also known as the rational function. Get that idea that ratio is in there. So ratios are fractions. So we get 1 over x. This is a hyperbola. So this would be something that those of you guys coming to Algebra 2 would not have been exposed to last year. So this would be the first time you guys have seen this. So you might notice that this one, the graph is made up of 2 pieces. Sometimes these are called branches of a hyperbola. It has 2 branches. So these lines here are called asymptotes. There's actually kind of a silentish P in there. So an asymptote is a line that the graph gets closer and closer to as it tends to infinity. So as we move up forever, that curve gets closer and closer to the y-axis, and as we head off to the right forever, the graph gets closer and closer to the x-axis. And same thing here, as we head to the left forever, it heads closer and closer to the x-axis, and as we head down forever, it heads closer and closer to the y-axis. So it's never actually going to cross there. So as I'm drawing those, I'm always trying to draw them like really close, but just kind of parallel along that line there. So you definitely don't want to see it kind of hook up or anything like that. You also don't want it to hook down as you're drawing it. Again, you're just doing a sketch right now. But as far as points I plotted to kind of help you out there, so if I plug in 1 divided by 1 is 1. If I plug in 2, so 1 divided by 2 is 1/2, so I'd plot it to the point 2 1/2. Now to get a point here, I plug it in 1/2. Well, 1 divided by 1/2 is 2. So I plot the points 1/2, 2. Over here it's just kind of the opposites of those. So -1 divided by -1, or 1 divided by -1 is -1. 1 divided by -1/2 is -2. And then 1 divided by -2 is -1/2. So those are the points I'm plotting there to kind of just get an idea of where it's going to be. For the rest, I would just kind of try to draw parallel to the x-axis, parallel to the y-axis. Start at the 1s, then try to curve it towards the x-axis, towards the y-axis. So the asymptotes, there's a vertical asymptote that's on the x-axis, or the y-axis, sorry. There's a horizontal asymptote that's on the x-axis. But notice the equations are switched, right? It's y equals 0 for that one, x equals 0 for this one. So this is the only one that doesn't touch 0, 0, but the kind of like the center of the graph is at 0, 0. This one also does not have a vertex. There's a couple of things about that since you guys have never seen that before, or some of you guys haven't. Then square root function, you guys definitely would have all had experience with this. This should look like a half parabola off to the side, or half curve off to the side is how I think of it. So you'll notice this one's the only one that doesn't have 2 arrows on it. So this is a hard stopping point here at 0, 0. So again, it's not a vertex, but has a starting point at 0, 0. Then of course the square root of 1 is 1. Square root of 4 is 2, and the square root of 9. So I don't know why I put that way over there, sorry. It should be there. Is it 3? Again, numbers that are easily square rootable. So 0, 1, 4, and 9 are numbers that are easily square rootable. Again, kind of a good idea to kind of know those as you're trying to graph some of these things later. Like, what's a number that's easy to plug in? So half curve off to the right. Again, only 1 arrow. Starting point, and then 1 arrow off to the right. It's a pretty flat curve also, so it doesn't like shoot up or anything like some of the other ones. It's pretty flat as it heads off to the right. And then we get the cube root, again another very flat curve. So how do I think about this one? That's stretched out S. So what am I seeing here? Not a vertex, but a starting or a center point here at 0, 0. The cube root of 1 is 1, and then the cube root of 8 is 2. The cube root of -1 is -1, and the cube root of -8 is -2. So again, numbers that are easily cube rootable. Again, just good to keep track of sometimes. Help you graph these things later. So what are x values I could plug in that are easily cube rootable? Every number has a cube root, but is it going to give you a nice answer? Right. The next cube root would be 27, so which is, again, it's not going to easily fit on a graph. So the stretched out S, this one goes off forever both directions. Again, a very flat curve as we head off to the right, because the next point would be at 27 to get all the way up to, just to get to 3, we'd have to head all the way to 27. Same thing down here. As you head off to the left, it turns out to be very flat. It should have a just slight little angle to it, but be pretty darn flat. So those are your parent functions, or your this one again. This textbook calls your toolkit functions. Again, I would recommend that you, or suggest that you start studying their shapes. Again, you're really going to want to know what they look like just by what the function is just by looking at the graph. So if you see like a v later, like okay, there's an absolute value, so then I can start working with that in transformations. Or if I see that vertical s, okay, that must be a cube function. So then I can start working that, or this split hyperbola. So again, the other side too is like when we're graphing later, you're graphing, supposed to be graphing quadratic, but then your graph starts to turn out like this. So you can kind of go, okay, something's going wrong here. I need to check on this. So, yep. So again, just like you guys to start studying those. We will be using them here for the next few lessons. So really would be just something you need to start doing. I don't have any particular questions I can give you though. I think in the past I've done a lot of pop quizzes with my students that have, so word-wise.